Okay, today we'll continue our exploration of the memory hierarchy. Last time we talked about virtual memory. Before that we talked a lot about DRAM as well as caches. And hopefully you have realized by now that memory takes long to access, right? And the access time, especially if you increase the frequency of the processor, if your memory takes, let's say, 50 nanoseconds to access, and if your processor is 5 gigahertz, you need to wait 250 cycles for memory access, right? And if there are multiple processors sharing the memory, then you may need to wait even more because these processors interfere with each other in the memory system, and we've looked at solutions to that problem. In fact, you had questions on the exam testing that, right? Now your latencies increase even more. The problem is soon your latency, your execution time becomes dominated by memory, right? Instead of processing instructions, the processor, the execution units that you have in the processor, the adder, the multiplier, the shifter, they would be waiting for data to operate on, right? And that reduces performance significantly. And people, researchers, as well as implementers, designers, have developed many mechanisms to try to alleviate this impact of long memory latency on performance. And we'll cover some of these techniques. Actually, you've seen some of this, right? The memory hierarchy exists because of that, right? You want a large memory, but building a large memory makes the latency too long, and you don't want that too long latency. So you built the memory hierarchy, like caches, DRAM, disk. All of that is designed to alleviate memory latency while getting everything else we want from memory. So we'll see other techniques today, actually some of which we've seen before. But before that, hopefully you're working on the homework. Actually, most of you finished it, I think, before today, right? And hopefully that was useful for the exam. And your lab assignment is due April 23rd, which is next Monday. Right. Have you started?
Yeah.
Yes.
It's extremely long.
You're done?
No, it's extremely long.
It's extremely long, really? There you go. It's good. Yes, it's long, very long. So you'd better start soon. But it's fun, hopefully. You'll build the memory hierarchy, right? You'll actually design a real hierarchy. So far, your hierarchy was toy, if you will. When you got a cache miss, you waited for 50 cycles and magically data appeared. Now you're going to make the data appear in a more realistic way, right? And you can do some extra credit as well, which is prefetching, which we will talk about today. Okay, but before that, I want to give out the prizes for the Lab 4 as well as Lab 5. Is everyone here? Eric is here, I know that. Arthur? How about Alex? Yeah, Alex is there. Good. We have 2. So Arthur, you'll pick your books and Arthur will get the whatever remains, I guess. And this is Lab 5 grades. I want to do these 2 things together. These are the grades for Lab 5. And this is, I think this is the perfect score, right, Chris? Yeah. These are fully correct implementations that got the full credit. There are 12 of them. And there is one more of it, one person who actually got the extra credit. So you can see that extra credit actually helps you. And that was Tyler. So he will get a book prize also, right? So he implemented the random replacement and had a nice analysis, 1-page analysis of how random replacement helps in some benchmarks and hurts in others, right? Which I thought was interesting and insightful. So he got the full 10% extra credit. Okay, so let me give these books, I guess. This time I will let you pick the books. So the first 2, Eric and Tyler, which books would you like to pick? There's the old book, The Structure of Scientific Revolutions. That's a very good book, actually. And there are 2 Feynman books this time. Surely you're joking, Mr. Feynman. Do you guys know this one? It's a famous book, right? I'd recommend you to read it. This is Feynman Lectures of Computation. Feynman was a physics professor. He was a physics researcher. He was a physicist, but he had a lot of ideas on computation as well. This is a deep book. And I have not read this book. This is Gödel, Escher, and Bach. I think Chris recommended this. Do you know this book? Okay.
I guess I'll take this one.
You'll take that one. Lectures on Computation. There you go. And Alex, which one would you like?
The left hand.
Left hand? Feynman? Okay. So Art is left with this one, I guess. So hopefully you'll enjoy the books. I don't know, are ebooks better these days for you guys? I cannot read ebooks, so I read real books.
It's nice for Kindle.
Nice for Kindle? Okay. Okay. As I said last lecture, we covered virtual memory, so hopefully you understand it well. Today, we'll cover memory latency tolerance, reduction, and prefetching. Actually, most of today and next lecture will be prefetching. So, we've covered latency tolerance before, right? Out-of-order processors tolerate latency. And an out-of-order processor tolerates latency by executing independent operations concurrently with a multi-cycle operation. Right? That's actually from a previous slide that I showed you. It's a little bit tweaked. When you have a long latency operation, multi-cycle, multiply, let's say, if you can find another independent instruction that can be executed concurrently with it, now you're amortizing the latency of both operations. Right? That's the idea of out-of-order execution. How do you do that? It does so by buffering instructions in reservation stations and reorder buffer, right? Remember, we put the instruction into the reservation station and figured out when it became executable, if you will, fireable, and then executed it when both of its sources became ready. And that's how you figure out which instructions are independent of each other or dependent of each other, and ensure that independent instructions can execute concurrently. So we call this the instruction window, so I'll define it here more concretely. These are the hardware resources needed to buffer all decoded but not yet committed instructions. And you know all these terms by now. Commit or retirement means an instruction can retire after it's the oldest instruction and after it's ready, right? Which means that it has executed and it's the oldest one. Why? Because we want to support precise exceptions, right? Does that make sense? Which means that you need the processor needs to buffer all instructions that have not yet retired yet at this point and that have been decoded. That's the window, if you will, that the processor looks into the future. And I'll show this with a slide. This is kind of your instruction window, if you will, abstractly. And you have, well, you can think of this as the reorder buffer as well, but it consists of other structures that contain everything related to the instructions execution as well. So this is the oldest instruction in the machine, and this is the youngest decoded instruction. And all of these instructions need to be buffered somewhere. And where are they buffered? They're in the reservation stations and the reorder buffer. Right? Because when you decode an instruction, you allocate a reorder buffer entry as well as a reservation station entry. And you deallocate the entry in order because you want to support in order retirement to support precise exceptions. And the oldest instruction gets retired, which means that it updates the architectural state when it finishes execution. Right. So the latency tolerance, well, okay, so this is the instruction window. What if you have a load instruction, let's say, that takes 500 cycles? Remember, we covered this before. What determines how much latency you can tolerate? How large of an instruction window do you need to actually ensure that you keep decoding while you're waiting for the result of this load? Right. If this is 500 cycles, and let's say you're fetching and decoding 4 instructions per cycle, in order to not stall, you need a window size that has 2,000 entries, right? While you're waiting for this load. Make sense? Well, it's nice maybe if you can build this. So building this turns out to be very hard because remember the reservation stations? What do you need to do in the reservation stations? Say it again?
Compare tag.
Exactly, compare tags. When an instruction finishes execution, it broadcasts its tag, and all of the dependent instructions need to capture that tag. If there's another instruction in the machine that is waiting for that tag, you need to be able to capture it, which means that for all of those entries in the reservation station, you need to have a comparator that compares the broadcast tag to the tag, source tags that are stored. In fact, two comparators, right, if you have two sources. So the number of comparators quickly gets out of control because you may actually be broadcasting multiple tags at the same time also, right? If you're executing multiple instructions at the same time. Right? You can actually do the calculation. Let's say you have a reservation station that has 2,000 entries. You have 2,000 entries. Let's say how many comparators do you need? Number of comparators. 2,000 entries in the reservation station. Let me do this in a better way. And now, for each broadcast tag, you need two comparators per entry, if you will, and also a broadcast tag. Let's say broadcast tag. And let's say your execution width, you have an execution width. That many tags can be broadcast in a cycle. So let's say your machine is 8 wide or 4 wide, let's say. You have 4 execution units that can complete 4 instructions in a given cycle. So you have 4 broadcast tags per cycle, right? So if you multiply this, what do you get? 16,000 comparators, right? That's quite a bit. And if you want to actually make your machine wider, execute more instructions per cycle, like 8, then this doubles. You have 32,000 comparators. Yes?
Why do you need 2 comparators per broadcast tag?
Oh, 2 comparators because you have 2 sources, right? An instruction can have 2 sources. That's the assumption we're making. Source 1 and source 2. You need 2 separate comparators. So this can become very expensive, right? So building a very large out-of-order machine is actually difficult because of this reason. And people have actually tried to optimize this a lot. I'm not going to go into those details. If you take 740, you will see some of those details. But you can be smart about it. You don't need to do all of the comparisons. You can eliminate some of them. And you can try to reduce the size of the reservation stations by being smart about how you allocate them. But still, in the end, if your latency is high, and the latencies are likely to get even higher, right? 500 cycles is a typical latency. To give you an example, Xbox, which is not the highest end processor, it had memory latencies of 650 cycles or so, or around that range. It of course depends on your processor cycle time as well, right? And the memory technology. You've seen all of this before. So if this becomes 1,000 cycles, this also doubles again, right? Assuming you don't want to stall. Okay, so this is so out-of-order execution cannot tolerate all of the latency. Why doesn't it tolerate latency? Because I've covered this, but I'll walk you through the slides also. When a long latency instruction, this load, is not complete, it blocks retirement because we need to maintain precise exceptions, which means we need to do in-order retirement. That's why we cannot continue. Which means that incoming instructions fill the window, and at some point your window becomes full. You cannot retire this. Your window is full. You cannot insert new instructions into your machine. And this is called a full window stall. And a full window stall prevents the processor from making progress in the execution of the program. Right? If you think about it, if you have an in-order processor, you still have some kind of window, right? Except it's very small. It's not, you could think of it as one instruction, potentially. If you pipeline it, it's more than one, but you could think of it that way. Whereas out-of-order execution enlarges this window by putting instructions to the reservation stations. So the problem exists in in-order and out-of-order processors. So just to give you an example, we'll use this example later on when we talk about run-ahead execution, but I'll use this to demonstrate the full window stall now. This is the load that we've been discussing more concretely. It takes hundreds of cycles, and let's say you have an 8-entry instruction window, 8 reservation stations in this case, and you have a branch that's dependent on the load. It cannot execute because the data is not ready. And let's say you have all other instructions independent. These independent instructions fill the window, and they get executed out of program order in an out-of-order machine, but they cannot be retired, right? But they still need to be buffered, right? Because you cannot retire them, and they have results. You need to store them somewhere. And younger instructions cannot be executed, right? Because there is no space in the instruction window. Let's say if you were able to put this load into the instruction window, maybe it could have been executed. In fact, maybe this load would have been another cache miss, and you could have executed and parallelized the 2 cache misses, right? But you cannot because you don't have space in your window. And the processor stalls until this L2 miss is serviced. We'll look at a way of actually building this window and still having a small window and still being able to execute this load. The idea is called run-ahead execution, and we'll get to that later on. Well, you can think about how to do that, for example. If you increase the window size, that's one way of tolerating the latency of this load. Then you can fetch this load, decode it, and execute it, and it turns out it's a cache miss, and those cache misses are serviced in parallel. Right? But what if you have a small window, and you want to do the same thing? Yes?
You could possibly have another copy of a register file that's only used as of these buffers. And that retires every certain cycles or something.
Okay, I think you're getting at something, but we can discuss that. Yeah. So somehow, basically, you're saying buffer these results somewhere else, and then take them away out of the window. Maybe, yeah. People have proposed things like that. Actually, that turns out to be a little bit complicated, because you need to now manage the ordering also between all of these instructions. And it's not this nice, right? There could be 1 independent instructions, 3 dependent instructions, and they could be interleaved with each other. Okay, so I'll show you some data. These are simulation results, but these are similar to a lot of data in existing processors. So if you look at an out-of-order machine today with a 128-entry window, these are this is the execution time averaged across many, actually, in this case, 147 memory-intensive workloads that actually exercise memory, access memory. I've broken down the execution time into 2 pieces here. Non-stall time and full window stall time. So if you look at this with, I think, 500 cycle memory latency, with some caching and actually some prefetching as well, what happens is only 30% or so of the time the processor is actually making progress, not stalling. Okay. Whereas, I think this is 68 or so. 68% of the time the processor is stalling. And if you go and analyze the simulation results, it turns out most of these stalls are because you have a load at the head of the instruction window that cannot retire. So that's the extent of the problem, L2 miss problem, if you will, or cache miss problem, or memory latency problem. The question is, how do you reduce this? How do you improve performance? So if you could actually eliminate all of this, all of these stalls, your performance would improve by 3x, right? Your execution time would go down to this green part. Make sense? So can we do that? So I'll give you a couple of major approaches, and we'll focus on prefetching. there are two major approaches, right? How do we actually tolerate these stalls due to memory? First of all, why do we have the stalls to begin with? Why can't we eliminate these stalls? Can we reduce them so that we never have to stall? That would be nice. And let's say we couldn't eliminate them. Can we tolerate the effect of a stall when it actually happens? In a sense, out-of-order execution is trying to do the latter, maybe, right? When you have a long latency cache miss here, 500 cycles, it tolerates the effect of that if you can build a large window, right? So sometimes the line between these two gets blurry, though. Do you eliminate the stall or do you tolerate the latency? Therefore, I will group these four techniques together. So how do you, actually, you've seen some of the techniques to eliminate stalls, right? Eliminate memory accesses. Any caching? Yeah, caching is the first fundamental technique to eliminate memory accesses, right? If you get a cache hit, you don't have 500 cycle latency anymore, depending on which level you hit, of course. Caching is one way. I'll give you the other ones, I guess. Yes.
Well, I was going to say you could combine writes.
Mm-hmm.
So if you have two writes to the same location, then the effect is just the same as having the last write.
That's right, yes. So writes are a little bit less critical, right? Because you don't really need the value to proceed. You can actually do the write, buffer it, and the memory can later do the write for you. You don't really need the cache block, if you will, right? So that's the main difference between reads and writes, actually. If you're doing a store, you don't really need to stall the processor. What you can do is, if this was a store, for example, what you could do is you could take this out of the window and record it somewhere, and that somewhere is called a write buffer in existing processors. Say, I have a store, it missed in the cache, and its address is this, its data value is this, and let's say that's the only thing you keep here. Now the processor can continue bringing instructions here, right, into the machine. So you don't need to actually stall the machine. But now if there's a load that comes, it needs to check that write buffer. Because the value may be actually there, right? Yes?
Doesn't that only allow you to have one more instruction? And you still have to wait for it to finish anyway?
One more instruction, meaning?
In your buffer.
Yes, but that can go also, right? Let's say you move the store out and it's enabled the addition of an add. Now your window can keep moving. Okay, let's say you have a store, add, multiply, add. And let's say these are all independent of the store. You remove the store, put it into the write buffer. Now you enabled one more instruction to come, but now your window can move. Meaning this add can be complete right away. Multiply can be complete. Multiply can be complete.
Does it have to wait for store to write back anyway?
No, right? Because the store is sitting in this write buffer. It's recorded. And it's the logic in the memory cache controller or the write buffer is handling that write. No other instruction needs that value, right? And if they need the value, that's what I was mentioning. If there's a load instruction that has the same address, then it gets the value from this buffer. Right. That's the idea of write buffering. Make sense? Yeah. So writes are less critical because you can actually take them out and buffer them. And this exists in existing processors. The store instructions do not stall the instruction window as much. Of course, when the write buffer gets full, this is a limited size buffer also, right? When it gets full, now you cannot put the store that is at the head of the instruction window here, which means that now stores actually can cause full window stalls as well. So if you have a lot of stores in your program and if your memory latency is high, you'd better have a large write buffer. Of course, now you know the trade-offs, right? If you make this write buffer too large, Now that could start affecting your cycle time, and you'll have comparators also here, right? Because if you have a load in your machine, you need to check whether its address matches. Okay? So you could alleviate the problem with stores a little bit. Okay, so caching, we've covered this. Prefetching is another technique to actually reduce or eliminate stalls. Multi-threading, we've covered this, right? This is actually a latency tolerance technique. When you have a long latency operation, execute something else from some other thread. An out-of-order execution. And many techniques have been developed to make these 4 techniques more effective also. Like we talked about how to improve the effectiveness of caches, right? How to reduce the conflict misses you get. You can increase the associativity. You can change the replacement policy to be more intelligent. Or you can try to randomize the index into your cache, right, with a hash function. Do you remember that we discussed that? Hopefully. Yes, some of you do. Okay. So let's take a look at these 4 techniques actually. These 4 techniques have been around for a long time, and you read the Wilkes paper. Caching, now that you know how it operates, it's very widely used. It's very simple, right? That's why it's very widely used. The idea is simple. It's effective, but it's a passive method, right? What do I mean by this? Basically, you need to first get a cache miss to bring the data into the cache, right? Which means that you cannot eliminate some misses. And we call these misses compulsory misses, right? The first time you see an access to a cache block, you have to wait. And also caches, remember, exploit temporal and spatial locality. And if you don't have that in your program, most programs do have it, but some programs do not, then if you're doing random accesses, for example, in memory, then caching is not useful, right? It cannot help. So for this reason, people have developed prefetching mechanisms. And this was initially in IBM 369091. That was one of the fastest machines of its time. And the idea here is basically before you get to an access, why don't you predict what you're going to access and bring it into the machine? Right? And IBM 369091 did this for its instruction buffers. So it had some instruction buffers, and instead of having a single instruction buffer like a normal pipeline machine would have, right, they would prefetch the next n instructions, if you will. Well, how do you do this? You know the program counter of the instruction that you just fetched, and since programs are usually sequential, right, in a control flow machine, the next instruction is very likely PC plus 4. Let's say your instruction sizes are 4. You know that the next instruction you're going to execute is the next sequential instruction in memory. And the next one is going to PC plus 8. Next one is going to be PC plus 12. So when I try to fetch an instruction at PC, address PC, why don't I bring in instructions at PC plus 4, PC plus 8, PC plus 12, ... and store them into this instruction buffer. That way, after I'm done decoding this instruction and that moves into the pipeline, I can just get this instruction. Right? That way you overlap the latency of fetches of multiple instructions. That was the prefetching IBM 369091 implemented. And we'll look at how this is done for data as well. So it turns out this works very well for regular memory access patterns, right? This is a very regular access pattern. Well, it's not fully regular, right? What if you had a branch somewhere here? Then your instruction buffer is not providing you the correct instructions anymore. So you'll have to take a stall in that case, right? Okay. And we will cover a lot today about prefetching. Multi-threading. Remember multi-threading? fine-grained multi-threading. You had a question on the exam. That actually tolerates latency, right? If you, in a sense, it tolerated the latency of stalls that are caused by dependencies, right? Because we fetched from a different thread every cycle. That way, no thread, you kept the pipeline full, except you kept the pipeline full from different threads, different applications. Does that make sense? So if one of the threads actually has a load instruction that misses in the cache, now you can execute instructions from other threads. That way you're still doing useful work and tolerating the latency. And this works well if there are multiple threads, right? We've discussed this. If there's only one thread in your machine, you're wasting a lot of execution bandwidth. There are actually two versions of it, versions of multi-threading. One is fine-grained multi-threading, as we discussed in class, right? Fetch from another thread every cycle, such that there are no instructions from the same thread in the pipeline at the same time, so that you don't need to do data dependency checking, you don't need to do branch prediction. That's the most purest form of multi-threading. And that way you tolerate any long latency operations that happen in any thread. The other is more coarser grained multi-threading. This is fine grained because you switch from one thread to the other in a very fine-grained manner, every cycle, right? But if you want to tolerate latency, especially the latency of these very long latency operations, you may do it in a more coarse-grained manner. Meaning, when this thread 1 gets a cache miss that's going to take 500 cycles, let's switch to another thread. Right? Instead of switching every cycle, switch to another thread when you get a cache miss. Make sense? And this is also called switch on event multi-threading, or switch on L2 miss multi-threading, if you will. And this is also implemented in processors. So examples, fine-grained multi-threading, Sun's Niagara processors are fine-grained multi-threaded today. Intel's Larrabee, I don't know if it exists anymore, but it's fine-grained multi-threaded. These are recent processors. Coarse-grained multi-threaded Intel Itanium 2 has actually sophisticated mechanisms for doing coarse-grained multi-threaded. When it gets a cache miss in its L3 cache, it switches to another thread. And it can have 2 threads, potentially, on the machine. Make sense? That way, if the other thread doesn't get a cache miss, you're still utilizing your machine, right? You're doing useful work. Okay. So that's another technique to tolerate latency. The downside is, of course, if you don't have multiple threads, or if you care about the performance of a single thread, this doesn't help, right? Because you care about the performance, switching to another thread actually doesn't help your performance. But we will see some techniques that use this kind of multi-threading hardware. So what does this require? This requires that you have multiple contexts, hardware contexts, present in the machine, right? Multiple register files, and you actually solve the problem in your first exam to make this work. You need to have multiple register files. You need to have multiple program counters. You need to switch between them. Coarse-grained multi-threading hardware support is similar, except you don't need to switch between the threads at the same time. You don't need to switch between threads in a very fine grain, right? Yes?
Can you have a memory hog situation in a situation similar to the memory hog situation in coarse-grained multi-threading? So one thread keeps executing, and the other thread waits for one thread to miss in L2 or L3, and it never misses. So won't that?
That's right. So actually, you're right. You could have something like that. That's why people have proposed mechanisms to prevent that. Yes. So if one thread doesn't miss at all, then there's a timeout employed. For example, Itanium 2 actually has this timeout. So that you haven't missed in your cache, but there's another thread that's waiting. So let me switch you out such that that other thread gets a chance to execute. That's a very good point, though. Okay. Okay, so we will see techniques that use this multi-threading hardware to actually improve performance of a single thread. So we will have multiple hardware contexts in the machine, but one thread will do prefetching for the main program. So if you care about only a single program, we'll execute that program, but we'll also execute what is called a helper thread, if you will, whose sole job is to prefetch data for this program. So you could use this multi-threading hardware to improve single-thread performance. And we will see one way of doing that. And you could do this in existing processors today. Actually, almost all processors today are multi-threaded. And maybe we'll get to that when we talk about simultaneous multi-threading. I'll throw you one more term here. Simultaneous multi-threading is the ability to execute from two threads at the same cycle. Right. So here, fine-grained, you switch between threads every cycle. Coarse-grained, you switch between threads every n cycles, where n is large, or every cache miss, for example. Simultaneous, you can actually execute from multiple threads at the same time, same cycle. You have two ALUs. One ALU could be executing an instruction from thread 1. Another ALU could be executing an instruction from thread 2. And a lot of processors today are designed this way. Of course, this is more complex, right? You can imagine. But we will see, hopefully, when we get to that lecture, how this is done. But this is another latency tolerance technique. This way, if one thread is not utilizing the other ALU, the other thread can utilize that ALU. Right? Of course, this requires a superscalar machine. Right? You need to be able to execute multiple instructions at the same time. Whereas fine-grained multi-threading requires just a pipeline machine. Right? Okay. Okay. Finally, we've just talked about out-of-order execution, right? Out-of-order execution tolerates the irregular cache misses. That's the main benefit, right? Irregular cache misses are hard to prefetch, and caching, by definition, it's a cache miss, right? Caching couldn't handle them. So out-of-order execution is able to tolerate those cache misses. But then it requires extensive hardware resources, as we just saw, for tolerating very long latencies. And we will see run-rate execution that alleviates this problem. And hopefully in the next lecture we'll get to that. But today I would like to focus on this part, which we have not looked at. And let's see if we get to all of this. So first of all, why do we prefetch? Why could it work? And I will talk about 4 questions. And prefetching actually can be done in many levels: software, hardware, and execution-based prefetching, which I have alluded to here. One thread doing prefetching for the other, for the main program. So what is the idea? The idea is simple, right? Basically fetch the data or instruction before a program actually gets to it, right? Before it's needed. Well, why? We've already figured it out, right? Memory latency is high. If we can actually prefetch the data accurately early enough, we can eliminate that latency so that we don't need to stall for this load. And we can also, this is a powerful idea because it can eliminate compulsory cache misses, right? Potentially, you don't need to see the address to actually predict that you're going to use the address. Does that make sense? Like I've already given you an example here, for example. The processor may have never executed PC+4, right? But when it gets to PC, the prediction is that the next instruction is going to be PC+4. And the prediction is that the next instructions are going to be sequential. Whereas those instructions may have never been seen, may have never been executed before. Right? So you exploit the access pattern, if you will. That's the idea of a memory access pattern. And if you can identify patterns in your memory accesses, you can actually prefetch data earlier for any block, if you will, that you have not seen. And we'll see under what conditions that's true. Right. So this can actually eliminate all misses also. If you have a capacity miss, doesn't matter, right? As long as your access pattern is regular. And if you know what to prefetch, you can eliminate, right? Does that make sense, or any questions on this? Okay. So one of the key issues is which address will be needed in the future, right? You cannot probably randomly pick an address. You need to figure out the access pattern. Of course, your access pattern needs to be predictable for this to work, right? In this case, it was predictable. We're going down an instruction stream that's sequential. If you're doing an array access, remember we did the vector processors? Array accesses are predictable. Vector accesses are predictable. You access the first element in the vector, you access the next one, next one, next one, next one, next one. And if these are stored sequentially in consecutive memory locations, you know exactly what memory locations you're going to need in the future, right? So you could go and prefetch earlier. So this works if programs have predictable misaddress patterns. Okay, here's a question for you. What if you predicted an address will be needed in the future, but that turned out to be not needed? Does this affect correctness?
No.
No?
I mean, you just wasted memory bandwidth, but now you're going to figure out that you need some other address and you're just going to load it as normal and you'll effectively just ignore the thing.
Exactly. So basically you can ignore what you fetched, right? You fetched the wrong thing. But that doesn't affect correctness because you didn't even use it for anything. So there is no need for state recovery in case of prefetching. You just prefetch the data, place it somewhere, and most processors place that prefetched data into caches today. And I'll give you an example of this. And if it doesn't get used, it gets evicted, right? So this is in contrast to other speculative execution methods. Let me back up a little bit. So prefetching is a method of speculative execution, right? You speculate, if you will. So what does speculative execution mean? Basically, it means doing something before you know that you need to do it. You speculate that you would need something, and you do it, but you don't know if you actually need it. Prefetching is like that, right? Branch prediction is also like that. You predict a branch before you know the direction, right? Before you really know the direction, you guess, if you will. Value prediction is also like that. But these are different because if you mispredicted a branch, you'd better recover, right? Does that make sense? You need to actually go back to the correct state in this case. Whereas with prefetching, that doesn't need to be there. So in a sense, prefetching is a little bit easier to implement because if you're wrong, in the worst case, you reduce performance but do not affect correctness. Okay, and in general, things that do affect correctness are harder to design because you really have to verify them very, very well, right? Otherwise, you can introduce a sophisticated branch predictor in your machine and your machine will not work. You don't care about performance if your thing doesn't function, right? Yes?
Shouldn't the recovery logic usually be pretty much the same despite like what your branch predictor is? So
that's right, yes. that was just an example. If you introduce a branch predictor to a machine that doesn't have a branch predictor, then you'll need to ensure correctness, right? But that's a good point. You're right. Recovery logic is usually the same. Okay. So some basics. In modern systems, so everything I will say in this lecture from now on will assume that you actually have a cache. That's a given. And prefetching is usually done in the cache block granularity. Meaning you look at the cache blocks that you miss. Here I showed you PC, but it's really the cache blocks you're going through when you're fetching instructions. Cache block 1, cache block 2, cache block 3, cache block 4. And you sequentially go through those cache blocks. Right? And machines do it that way today. It can reduce both miss rate and miss latency. Hopefully this is clear. So when you prefetch something, by the time you use it, it may have already arrived into the cache. Right? That way you've eliminated the entire miss. But a prefetcher may generate an address for a cache block, and that cache block may be pending when the processor actually needs that cache block. Right? In that case, miss rate doesn't reduce, but miss latency reduces because the cache block that's needed by the processor is in transit, if you will. And the processor doesn't need to generate another access to that cache block, meaning generate another miss. Remember, miss buffers, miss status handling registers? If a prefetcher actually generates a cache miss, it places the address of the block into one of the miss status handling registers. And when the core processor, let's say the prefetcher, generates an address to cache block A, and processor also needs A, processor searches this MSHR and figures out, oh, somebody already generated a request for A. So it's not going to generate another request for A. Right? Now we're putting things together. So these MSHRs are useful for merging the requests between prefetcher and core as well. Okay. Prefetching, well, as I told you, it can be done by hardware, compiler, or programmer. Let me give you just one example prefetcher. And this is one of the most commonly used prefetchers in existing systems. If you look at this kind of a cartoon of a processor, or memory hierarchy, if you will, processor somewhere here. You have the I cache, you have the D cache. These feed into the L2 request queue, and you have the L2 cache. L2 misses and writebacks go to the bus request queue, and you have a bus and memory controller. This is, I guess this is kind of an old system where memory controller is off chip. And the memory controller controls the memory banks. So a prefetcher could be actually placed anywhere, but let's place it here. In this case, I call this a hardware stream prefetcher. And the idea of a stream prefetcher is to detect streaming accesses. Accesses like this. Address A, next cache block is access address A plus 1, next cache block A plus 2, A plus 3, A plus 4, dot, dot, dot. And you can imagine it's easy to detect, right? So it sits between the data cache and the L2 cache, and it looks at the cache misses coming out of the data cache. And if it sees a pattern, it generates a prefetch, and it inserts that prefetch into the request queue here, such that that prefetch request is handled by the memory hierarchy, just like a normal demand request, except the difference is you have a bit saying this is a prefetch request, right? So that the result doesn't go all the way into the registers. Does that make sense? So you could place this anywhere really, right? You could actually, the instruction prefetcher could be looking at I cache misses here. In fact, in this case, this is also looking at I cache misses. Or you could have a prefetcher at the memory controller, right? That looks at what accesses come here, and based on that detects patterns, and then prefetches data from the memory banks. And there are trade-offs associated with this. You could place it at the processor level, right? You look at the prefetcher hardware can try to detect patterns coming directly from the processor instead of the misses that are filtered, if you will, by the caches. And there are trade-offs associated with it. Right? So one trade-off, if you place the prefetcher here, if it looks at every single load and store, let's say you still operate on the cache block address, you can see the full access pattern of the processor. Right? Whereas if the prefetcher is looking at the accesses that miss in the data cache, then it's not the full access pattern anymore, because some accesses hit in the data cache. So you may not have full information. So your prefetching accuracy may degrade. And we'll see what the I guess we'll see what some of those design choices lead to. Any questions? Yes.
Should we have one at multiple levels? Should we have
So you could actually. You could have. In fact, some of the processors today have that. Intel processors have prefetchers at the L1 level, L2 level, and the memory level as well. And they could detect different access patterns. And they could be different kind of prefetchers also. So you could customize the instruction prefetcher to be more sequential. Right. Yes?
So the prefetcher needs to know what the state of the cache is, right? In order to determine if it needs to actually go and fetch.
So in this case, it doesn't need to. So if you look at this, what it does is it looks at the cache misses. Let's say your cache misses look like this. You record A plus 1, A plus 2, and then the prefetcher says, oh, okay, I have a streaming pattern. I'm going to prefetch A plus 3. It doesn't need to know whether A plus 3 is in the cache or not. It's predicting that it's not in the cache. So it inserts a request into the cache. And let's say it initiates the prefetch of access address A plus 3. This A plus 3 is checked in the cache first. And if it misses in the cache, then you generate a request. So it's just handled like another request that goes through the hierarchy.
So all it does is generate more requests.
Exactly. Exactly. It generates more requests. Yes?
Does the memory controller give the prefetch requests lower priority as compared to requests like from the cache?
Oh, that's a good question too. How do you once you insert prefetches into the entire system, what should their priority be compared to demand requests, right? Because the processor is also making demand requests that are not generated by the prefetcher. Well, the answer is it depends. So many processors today, well, I shouldn't say that. Some processors actually prioritize the demand requests over prefetch requests. Some processors do not distinguish between them. It turns out the right answer is somehow figuring out which one is better and having an adaptive priority. Sometimes prioritizing the prefetch requests if the prefetcher is doing well, and deprioritizing its requests if it's not doing well. That's not done today. But sometimes prioritizing prefetch requests is okay, or treating them the same priority as the demand requests could be okay, right? Why? What if a prefetch request hits in the row buffer, for example, and a demand request misses in the row buffer? And if your prefetch turns out to be accurate, then you would like to do that prefetch quickly and then do the demand, right? Because if the prefetch becomes a row conflict, then it affects your performance even worse. Okay? Yes?
So what I was thinking was, since if you have a sequential prefetcher, it's gonna pretty much hog the memory control and keep getting hits every time. That's why like the demand accesses will be stalled in the memory.
I see. Demand accesses from the same application?
Yeah.
Yes, so that could also happen. That's right. You're right. That's why prioritization is important. Okay, yes.
So shouldn't we have like a prefetch method in which like the lowest level of the cache fetches for something like say 100 instructions down the line, and then one level above fetches say 50, and like that you can have a hit all the way through.
Potentially, yeah. If you can actually feed the pipeline. If your access patterns are regular, you could do that. Something like that.
But wouldn't implementing something like that create have a requirement for a heavy bandwidth down the stream? But you don't have that. We have that kind of heavy bandwidth up the stream. So wouldn't that be a conflict?
Yeah, you have more bandwidth here, you're saying, and you have less bandwidth
but
here.
Implementing something like this will cause more bandwidth requirement down there. So
Potentially, yeah, potentially. But prefetching, yes. If you're inaccurate, what happens is you waste bandwidth also, right? If you're fully accurate, you try to utilize the bandwidth at the same time. Okay, so there are 4 key questions in prefetching, and we'll try to cover quite a few of them. First of all, what addresses to prefetch? When do you initiate a prefetch request? You were kind of getting at that. Because if, like, when should you start prefetching address A plus 3, for example? Right. Here, for example, when you get to this cache block, when you're actually executing instructions from this cache block, maybe you're already too late to prefetch, right? If it takes 100 cycles to prefetch the next cache block, you're going to be done executing instructions within this cache block in a few cycles anyway, right? So you'd better prefetch a little bit ahead. So which means that when you get to, let me call this the cache block, I guess. When you're actually prefetching cache block C, when you're actually executing instructions from cache block C, maybe you should actually prefetch from cache block C plus 16, right? When you get to execute instructions from C plus 1, you prefetch from C plus 17, right? That way you maintain a distance between the processor access stream and the prefetcher. Where do you place the prefetch data? That's another question, right? You have all these structures here. Where should you place them? And how do you do the prefetching? So let's take a look at the what first. Actually, we'll cover this more. What addresses to prefetch is important because if you prefetch useless data, you waste resources, right? Memory bandwidth, cache or prefetch buffer space, depending on where you place the data, energy consumption. And if you're prefetching something useless, yes, you don't affect correctness, but you do affect all of these things that are potentially very precious, right? In your cell phone, for example, you don't want to have a terrible prefetcher. Your battery can drain because of that. Think about a prefetcher that has 1% accuracy. Would you like that on your cell phone? I don't know. Maybe you do. If your performance is really critical, potentially, right? If you have 1% accuracy. But sometimes energy is important, and remember, energy, if you generate prefetch requests all the way down to the memory controller, these buses are very wide buses as well as thick buses. They consume a lot of energy, right? They have a lot of capacitance. Okay. And all of these resources could otherwise be utilized by demand requests or more accurate prefetch requests. So prefetching what addresses to prefetch, that decision is of first order importance. And we'll see different methods of doing that. So accurate prediction, prefetch accuracy, well, this is nothing complicated. What is an accurate prefetch? An accurate prefetch is a prefetch that's used later, that's requested later by the processor. And you can compute prefetch accuracy by counting the number of prefetches that are later used and dividing that by the number of prefetches that are generated by the prefetcher. Right? Ideally, you would like to have 100% accuracy. Right? So how do you know what to prefetch? You can predict based on past access patterns like this. Or you could use the compiler's knowledge of the data structures. Right? If the programmer knows something about the semantics of what they're going to access, they can potentially say to the hardware, prefetch this instruction while I'm doing this. Right? And we'll take a look at that. You can imagine that, right? When you're doing some work on one data structure, the programmer knows the next data structure that's going to be accessed is going to be this other data structure, and the programmer can insert a prefetch instruction for that data structure, right?
Databases do something similar to this on disk. So like if they're trying to sort things, they do like a merge sort type approach where they read in like a certain number of buffers, and then while they sort that in memory, now they're reading the next number of buffers.
Exactly, yes. Exactly. So if the programmer knows that, and if the programmer actually cares, then they can insert such instructions, such code into the program. And prefetching algorithm determines what to prefetch. Well, I guess the programmer has a prefetching algorithm in their mind also when they write the programs. I know, have you guys written programs with prefetch instructions? No? Not yet? Maybe after this lecture? Okay. Okay, we'll get back to this what. In fact, we'll spend most of our time on that what. So when do you initiate a prefetch request? That's another, yes?
Can't you use branch prediction that is used elsewhere to predict what to prefetch?
So for example, if you're doing instruction prefetching,
So
if you know the branch predictions, perhaps you can predict what to prefetch next, you're saying?
yeah, because effectively if you're predicting that branch to take, and if you're going to execute that, then might as well you incorporate that here as well.
That's right. So you could do that. That's right. And there have been proposals like that. But let's discuss that later on. You could actually use that effectively for instruction prefetching. But let me not get into that right now. If you remind me later on, maybe we'll discuss that. There are some processors, like IBM processors, that follow the branch predictor to actually prefetch data into the instruction cache. So they run the branch predictor ahead, if you will. Your pipeline can be stalled, but your front end in the machine could be running. Right? Does that make sense? You could imagine something like that. But if you remind me later, we can get back to it. Okay, we're talking about when. When to initiate a prefetch request is important, because if you actually generate a prefetch request too early, by the time the processor needs it, it may be out of your buffers, right? It may be out of your cache. It may have already been evicted. That means even though the prefetch was accurate, you couldn't take advantage of it because you were too early, right? If the prefetch is too late, well, you prefetch cache block A, and it's going to take 500 cycles to bring it, but in the next cycle, the processor needs it. That's a too late prefetch, right? So you don't want to do either of these. You want to prefetch data such that it's needed by the processor right when it arrives from the memory system. And this turns out to be a difficult problem, right? How do you actually figure that out? So it's not only what address to prefetch, but when do you prefetch it? That's important. So this is called the timeliness of the prefetcher. A prefetch is timely if it is actually in the cache when it's needed. It can be made more timely. A prefetcher can be made more timely by becoming more aggressive, right? So here, for example, if the processor is working on cache block C, prefetching cache block C plus 1 may not be timely, right? Because in the next cycle, the processor is going to access it, probably. Whereas prefetching cache block, let's say C plus 100, may be too aggressive, if you will, right? You're predicting that your sequential stream will go up to cache block C plus 100 cache blocks, right? Let's say you prefetched it, but you may never actually get to use it, right? Because you take a branch in the middle to somewhere else. Okay? So the aggressiveness is essentially how far ahead is the prefetcher from the demand access stream. This is the demand access stream is the, I'm throwing you terminology here, but hopefully that's relatively simple terminology. These are the demand accesses, actual load store accesses made by the processor, cache miss accesses. If the prefetcher is far ahead from the processor, then it's too aggressive, right? But that also makes it more timely potentially, right? So there's another trade-off here. If you're too aggressive, you may be more timely, but you may not be accurate, right? Does that make sense? Because you want to be timely, you don't want to prefetch too early, so you prefetch far ahead, but the processor may never get to it. So there are trade-offs associated with prefetching, and this is the trade-off between timeliness and aggressiveness, timeliness and accuracy. Similarly, the software can move the prefetch instructions earlier in the code, right? A prefetch instruction, you can pull it earlier. So let's say this is your code, and you have a load instruction here that somehow the software figured out that it misses in the cache. So the software inserted the prefetch instruction here. If this latency is, let's say, 100 cycles, and if it takes 100 cycles to execute all of these instructions here, and if the memory latency is 100 cycles, then this is a perfectly timely prefetch. Right. But let's say the memory latency is actually 500 cycles, then you may want to move the prefetch earlier in the code. The downside is you do the prefetch here for this load. Somehow you need to generate the address, of course. But again, this load may never be executed, right? You may take a branch that never executes the load. That way, you try to improve your timeliness by moving the prefetch earlier, but now you generate a useless prefetch because you moved the prefetch too early. Right? Because the code will never get to the load that you're prefetching for. Yes?
You have a prefetcher that's dedicated to your instruction cache. And you make it as aggressive as possible. And like it's big enough to hide the latency of like any possible miss. Then it doesn't matter if it's inaccurate, right? Because like you can be inaccurate, but you're always going to have the next available address to go to.
Well,
the next available instruction will always be there in your cache.
Assuming you have infinite cache space, right? Or large enough cache space, I would say. Because if you're very aggressive now, you have limited space to buffer your prefetches also. Where do you buffer them? Okay. Yes? Well.
So theoretically, when is actually quite solvable, right? It's just what is that's not solvable. If you know your cache, if you know your instruction set, theoretically you can solve when perfectly, but it's just what that you cannot solve perfectly.
So that's not necessarily true, right? What may be a little bit harder, but when is also very hard because you cannot predict all the latencies in the memory system, right?
True.
You don't know. In fact, this becomes even harder when you have multiple different applications. Right? You have some other application that's actually executing in the memory system. You have no idea how long it'll take for this program to access a location. Right? So it's actually a very difficult problem.
Another question.
Okay, very quickly.
When you talked about passing through a program initially, the prefetching program, couldn't it actually go in and check the data as well and set up instructions to check at this critical point it's going to use this data to make a branch decision and effectively load that data out first and predict your branch with actual data that it's going to use? It's basically like a multiple pass through program.
Oh, I see. So if you actually execute the program in that case,
just come through, check the data. This data is, if it's just data on disk.
Yeah, let's get back to that later. You could imagine doing fancy things like that, and maybe we'll cover some of that later on. Okay. Okay. So the next challenge is where do you actually place the prefetch data? Right. You could do it in the cache, or you could have a separate prefetch buffer. In fact, existing processors employ both, if you will. In cache, it's simple design, right? There's no need for a separate buffer. But the downside is you know already, right? Now you can evict useful demand data. Right? You could pollute the cache, if you will, with something that you prefetched. And you don't know if this is useful. Well, you don't actually know if the demand data is useful also, right? Because you don't know if it'll be used. But it was used previously. If you put it in a separate prefetch buffer, now the demand data is protected from prefetches, right? There's no cache pollution, if you will, for the data that was in the cache. But now you have a more complex memory system design. Right? Adding another buffer into the memory system makes it hard. So because there are a lot of questions, right? Where do you place the prefetch buffer? First of all, do you place it at the L1 level, L2 level? Do you have a prefetch buffer for each levels? Well, you can think about the trade-offs associated again. When do you access the prefetch buffer? Let's say you place the prefetch buffer next to your L2 cache. Do you access those two structures in parallel or serially? Do you or when do you move the data from prefetch buffer into the cache? Right? How do you manage that data? How do you size your prefetch buffer? And I'll skip this. When we cover coherence, you will see that. So many modern systems, because of the complexity that prefetch buffers add into the system, they place prefetch data into the cache. So if you actually read the manuals, they'll tell you. I guess these are some of the old ones, but the new ones are like that too. Prefetching into the cache is easy because you already have all of the paths for demands anyway. All of the wiring for demands anyway, and you can place the prefetch cache blocks into your cache as well. Okay, one more thing before we go into algorithms, or maybe there are a couple more also. Which level of cache do you prefetch into, right? Into the L2 cache, into the L1 cache, or do you actually prefetch from between the hierarchies as well? In fact, there are separate prefetchers between levels today. And where do you place the prefetch data in the cache? Right. Another design choice for you. One of you mentioned that how do you prioritize between demands and prefetches? That question comes up not only at the memory controller, but also in the cache, right? Do you actually treat the prefetch blocks the same as your demand fetch blocks? Prefetch blocks are not known to be needed. And if you have an LRU policy, you know that a demand block is placed in the MRU, most recently used position, right, when you fetch it. But when you prefetch a block, do you change the replacement policy such that it favors the demand fetch blocks? There have been processors that did that. I think one of the HP processors, what they did was for prefetch data, place the data into the LRU position, least recently used position. So don't mark it as the most recently used. Well, it wasn't used anyway, it was prefetched. So in a set, place into the least recently used position. That way you reduce the effect of prefetches on demands. But this may not be a good decision also, right? Because what if your prefetch is actually accurate and useful? Okay, so you see the design choices. Where do you place the hardware prefetcher in the memory hierarchy? We've already talked about this, right? What access patterns does the prefetcher see? If you actually see a more complete access pattern, again, potentially you can get better accuracy. We haven't defined coverage, but coverage is simple also. What fraction of the cache misses can you actually eliminate? Can you actually prefetch? That's the coverage of a prefetcher. And if you see a more complete access pattern, it's likely that you're going to get better accuracy and coverage. But the downside is, if you put your prefetcher to look at L1 hits, if you will, which is right at the beginning of L1 cache, then the prefetcher now needs to examine more requests, right? Which means that there may need to be more ports into the prefetcher, right? Which means that it's a more complex structure. Okay, so let's take a look at how also. Any questions so far? Okay. I told you that there are three major ways. Software prefetching. In this case, the ISA provides prefetch instructions to the programmer. And the programmer or compiler inserts these prefetch instructions, which means that they need to put some effort into where to prefetch, where to place these instructions, right? The advantage is if the compiler or the programmer knows the access pattern, knows some semantic information about the access pattern, they can do a much better job in prefetching, right? Again, remember the data structure. If you're actually traversing this data structure here, and you know that you're going to access this next data structure, you can generate a prefetch instruction for this data structure before the code that actually searches this one, right? You could have a function search that searches something in this data structure. In the meantime, you can generate a prefetch instruction here. Of course, now the compiler or the programmer needs to know how big the cache is, right? What if the data you access in this data structure is huge? By prefetching data from this data structure, you may actually be polluting the cache, right? Okay, so it's not that easy, if you will, especially for complicated patterns. And that's why this usually works well for regular access patterns, as I'll show you an example of. Hardware prefetching. In this case, hardware monitors the accesses from the processor, as we've seen, and memorizes or finds patterns or strides, if you will. You already know the notion of a stride, right? That's essentially the distance between the elements of a vector. In this case, you could think of this as a vector. It's not a vector, really, but the access pattern, there's a stride in the access pattern, right? And the stride is one cache block. could be basically the stride in the access pattern is defined similarly to a stride in the vector. It's the distance between consecutive accesses to memory. Okay. This could have been A plus 15, A plus 30, A plus 45. You know, in that case, that's a stride. And the hardware can learn this, right? Or memorize it, if you will. By just looking at what was the distance between multiple consecutive previous addresses. Hardware can do the calculations. Right. It can record the last access and check what is the address, what is the distance between the current access and the last access. Record that. Now record A plus 15. That's the last address. And the current address, A plus 30. The distance is 15. Does it match the previous recording distance? It does match, right? Now you have a stride. And you could become more confident as you see 15. The hardware can keep counters. How many times have I seen 15 as the distance between the current access and the previous access? And if it has seen 15 enough times, it can say, oh, it can be confident that this program is actually striding through memory. So let me start prefetching, assuming a stride of 15, right? So that's one algorithm, if you will. I gave you one algorithm. I didn't give you exact implementation details, but you can imagine this is relatively simple hardware. You have a subtractor, if you will, that subtracts the address of the current address, current miss, from the address of the previous miss that was seen, and records that stride or delta, if you will, in some hardware structure, and compares it to the previously seen delta, right? And also maybe a few counters, another counter telling how many times you've seen this delta consecutively. And if that counter is greater than some number, then the prefetcher can say, I'm confident that I'm striding through memory with a stride of this delta. And now I'm going to start prefetching. If the last access was, let's say, to A plus 45, I'm going to prefetch A plus 60. And another design decision would be, maybe I'm not going to prefetch only A plus 60, but I'm also going to prefetch A plus 75, A plus 90, A plus 105. Assuming that I'm striding, the program is striding through memory. That's relatively easy to build, and this is called a stride prefetcher. That way you can capture the regular access pattern. That's one way of memorizing or finding patterns and strides. And generates prefetch addresses automatically in hardware. Right. There are also execution-based prefetchers. I briefly alluded to this. You can execute a thread to prefetch data for the main program. And we will see this. And this thread can be generated by either the programmer and more ambitiously in hardware also. That's more hardware cost. But we'll see one way of actually doing this in a simple way. Basically executing the program to generate prefetches. Executing a piece of the program to generate prefetches. Have you ever done that when you programmed? Probably not. Okay, so software prefetching. The idea is compiler or the programmer places prefetch instructions into appropriate places in the code. And you can read Todd Maury's paper on that. That's one of the first papers. Prefetch instructions prefetch data into caches. And we already talked about that. So what is an example of an instruction? These actually do exist in current processors. This is from an old x86 manual, I think. Well, it's prefetch H, prefetch data into caches. And it's microarchitecture dependent specification. Basically, the programmer or the compiler provides an address with an addressing mode. And, well, you can read it here, right? Fetches the line of data from memory that contains a byte specified with the source operand to a location in the cache hierarchy specified by a locality hint. if you say T0, prefetch T0, prefetch data into all levels of the cache hierarchy, right? And this is also actually microarchitecture dependent, apparently. In the Pentium 3 processor, it can be prefetched into first or second level cache. In the Pentium 4 and Intel Xeon processors, it is prefetched into second level cache. Okay, so if you have T1, then the data goes into the second level cache. So you can see these instructions are actually used by the compilers today. So if you actually compile with GCC, GCC can insert prefetch instructions with some of the algorithms similar to described in the paper. Okay, so why does it make sense? So if you look at this, I just kind of gave you a prefetch instructions, if you will. This is, you're traversing through an array. I guess this is the dot product of two arrays. Is that true? A and B? Yeah. The access pattern is very regular, right? And assume that these are all cache misses for now. Basically, you know that you'll access the next element in the next iteration, in this case. And in this case, the inserted prefetch instructions are prefetching 8 iterations ahead. Right? You're going to access I plus 8 iterations after you access I. Right? Does that make sense? And there are 2 prefetch instructions. This way, if your memory latency is on par with 8 iterations of execution, you get the data right at the time you need it. Right? So that's the trade-off the compiler somehow needs to make. Figure out how many iterations ahead should it generate these prefetch instructions for. And that could be difficult, as we were talking about, because that latency is not constant. Right? That latency depends on what else is executing in the machine, which makes it tough. Okay, so there are issues here. The advantage, of course, is if you can do this, this is great, right? You overlapped all of, you hid all of your memory latency because you prefetch data by the time you need it. There are downsides. Now you have prefetch instructions which take up processing bandwidth, right? They will be part of your instruction window. I erased the instruction window over there. They will actually be part of your instruction window. You will have prefetch instructions in here, right? So that's one downside. How early to prefetch? Determining this is difficult, and we've already talked about this. But just to give you an idea of the difficulty, this is the distance of the prefetcher. The distance is how many iterations ahead is it prefetching for. Determining this distance is dependent on the cache size, how long does it take to execute each loop iteration, what is your memory latency. Right? In fact, we could have a homework question that figures out, lets you determine this distance. And this is very dependent on the microarchitecture of the processor. You generate code with prefetch instructions on one machine, for one machine. It has one cache size, one memory hierarchy. You run that program on another machine with a separate cache size. You see that actually prefetching slows down the program. Right? Because whatever used to be a miss in this machine that you generated the code for now becomes a hit in this machine that you're running the code on. Because this second machine's cache may be much bigger. Right? And these prefetch instructions are useless. And they occupy machine resources, so you lose performance. So that's one of the disadvantages of doing it at the software level. Right? Your code portability, performance portability, if you will, is not good. What you optimize for one machine is not optimized for another machine. And we've already figured out that going too far back in the program, if you will, putting this prefetch instruction too early in the program reduces your accuracy. Also, you need special instructions in the ISA for prefetching, as we've seen in x86. Although there are machines that actually circumvented this. For example, in alpha, a load into register 31 is treated as a prefetch, because register 31 is always hardwired to 0. So they got away with that, that you didn't need a separate instruction. But other like x86 has a prefetch instruction, and PowerPC has a similar instruction, which is a different name. This is also not easy to do pointer-based data structure. So if you want to do software prefetching, I'll leave you with this. I'm not going to go into that much detail. But how do you prefetch pointer linked list accesses? This is a linked list access here, right? So while P, you're doing some work on the pointer, and then you're going to the next element linked from this node. If you do this, does it work? Prefetch P next? Well, I don't know. Can you do this? P next, next, next?
You're going to get a seg fault.
Well, you could. That's right. Yeah, ignore the seg fault part. That's right. Well, exactly. Actually, that makes it harder. Also, you need to check whether or not you actually get a null pointer. Also, right. So the issue is, if you're going to get a cache miss on any of these, let's say you don't get a seg fault. If you're going to get a cache miss on any of these, then you're going to stall the machine anyway with the prefetch instruction, right? Which means that prefetch instruction needs to wait. There's a dependence on the prefetch instructions, which means that you cannot now retire the prefetch instruction, right? Yes?
Doesn't it also depend on how long the work part is?
That's right. It also depends on the work part. So this could potentially work if the work is large, right? But if the work is small, let's say, then you want to really prefetch many iterations ahead. And that's very difficult to do because now your prefetches next pointer is dependent on the previous iteration, right? It's not like this. Here, n iterations ahead is not dependent on the current iteration. Okay? Okay. So where should a compiler insert the prefetches? We've talked about this briefly. Prefetch for every load access, that's not a good idea, right? This is too bandwidth intensive. Ideally, you would like to profile the code and determine the loads that are likely to miss, right? And we already covered this many times. The downside of this is profile input set may not be representative, right? Which means that you think that a load misses based on the profile input set, but at runtime the load doesn't miss. You inserted prefetch instructions. Now you wasted a lot of execution time. That's another disadvantage of doing it at the software level. How far ahead before the miss should the prefetch be inserted? And again, you can profile and determine the probability. Actually, you could have a more sophisticated profiling mechanism. Let's say you figured out this load misses a lot. You could insert the prefetch in some location and profile the execution time. And then insert the prefetch in another location and profile the execution time. And try to figure out what is the best distance, right? That's one empirical way of trying to figure out the best distance. It requires a lot of profiling runs, of course. But again, the downside is profile input set may not be representative. And you usually need to insert a prefetch far in advance of hundreds of cycles to cover the latency of hundreds of cycles, right? And that reduces the accuracy at the software level. Okay. But that said, for regular access patterns, software prefetching is very useful, and compilers today do this kind of prefetching. And if you're an ambitious programmer who cares about the performance of your code, you would probably do that prefetching also. And people do that kind of prefetching. Hardware prefetching. Now you need specialized hardware. The idea is you have specialized hardware that looks at the access patterns and prefetches data based on path behavior. The advantage of this is now you can tune this to system implementation, right? You're not changing the program. You actually have these specialized hardware, and you can tune it to the machine's memory system configuration, right? Because the designer knows the memory system configuration. The other advantage over software prefetching, it doesn't waste instruction execution bandwidth, right? You don't have prefetch instructions in your window. This happens only in the memory hierarchy, but you still waste memory bandwidth potentially, right? If you're wrong, especially. Well, there are other advantages compared to software. The regular software hardware disadvantages and advantages that we've covered, right? One example, you're not dependent on profiling anymore, right? You can see the dynamic access pattern as it happens in hardware. The downside, of course, is now you have more hardware complexity to detect patterns. Especially for easily detectable patterns, software can be more efficient, right? If you're doing an array traversal, for example. Okay. What are some of the algorithms? I've actually given you the more complicated algorithms, like the strike prefetching that we discussed, so I'm going to go through these relatively quickly. Simplest form of hardware prefetching is actually always prefetch the next cache block. You touch cache block A, always prefetch A plus 1. Or always prefetch next n cache blocks, if you will. These are called next block or next line prefetchers. Or a next sequential prefetcher. It's very simple to implement. No need for sophisticated pattern detection, right? And works well for sequential access patterns. You don't need to detect the pattern, right? You don't need to detect actually that you're touching the next cache block. You just always prefetch next n cache blocks. And works nicely for instruction prefetching. This is what IBM's 36091 prefetcher did for instruction buffer prefetching. The downside is it can waste bandwidth with irregular patterns, right? Well, I guess here's a quiz for you. What is the prefetch accuracy if your stride is 2, the processor is actually accessing blocks with stride 2, and you always prefetch the next line? Zero. Who says 0%? Yes, 0, right? Because the processor's access stream is like this: A plus 2, A plus 4, A plus 6, and the prefetcher, when it sees A, it prefetches A plus 1. When it sees A plus 2, it prefetches A plus 3. When it sees A plus 4, it prefetches A plus 5. It's always wrong, right? It's wasting bandwidth. It's not accurate. Of course, if your n was 2, then you would prefetch A plus 2. Then you are 50% accurate, right? But then you're still wasting bandwidth. Of course, I'm not talking about time limits here. Also, you may not always be going upward, right? You could be going backward also. What if you're going A minus 2, A minus 4, A minus 6? So quickly this becomes not very accurate. That's why people have moved to prefetchers like strike prefetchers. And there are two kinds of this. One could be program counter based, one is cache block address based. What I described to you here was based on the cache block addresses, right? Based on the cache blocks that miss in the cache, the hardware detects the stride, right? But you could do this based on the program counter also, based on the load, right? And we'll take a look at that. So the simple idea, regardless of what kind of strike prefetcher you have, is record the distance between the memory addresses that are referenced and use that as your stride, right? So if you do this on an instruction-based way, the way you record the distance is you record the distance between the memory addresses referenced by the same instruction. Right? You have a load at program counter X. You keep track of what is the memory address that was cache block address that was touched by this load, and what is the current cache block address that's being touched by this load, and you record a stride. And the next time you execute the same load, you prefetch last address plus stride. It's simple, right? Yes? Okay. And this is one way of building it. I'm not going to go into this in that much detail. So if you look at this, you have a load instruction, program counter, and the last address referenced, and the last stride, and you have the current address. You compare the current address to the last address. You have a distance, and you look at the last stride. If they match, then you can increment the confidence counter, saying that this is how many times I've seen the stride consecutively. Right? That's the idea. Of course, you have timeliness issues with this. Basically, if you initiate the prefetch when the load is fetched the next time, it's too late, because load will access the data cache soon after it's fetched. So what do? Basically, you can prefetch ahead, right? Instead of just prefetching whatever I said here, last address plus stride, prefetch last address plus n times stride, right? That's and there are other ways of doing this, but I'll not go into that. Actually, look at PC, one of you mentioned. You could run your branch predictor ahead and generate the generate prefetch addresses using the stride prefetcher. Okay, so cache block address space, this is what I described earlier, and I will not go into detail here. So you can read the paper that I'm going to mention here. So this is called a stream buffer, and it's essentially a stride prefetcher that works for a stride of 1, if you will. Actually, it's a little bit simpler than that. It assumes that you're streaming through memory. And this is implemented in many processors today, more sophisticated forms. And we can put up the paper so that everyone can look at it. I guess I'm not going to require the reading, but the idea is you have these stream buffers that come after the cache, and each of them holds a stream of cache blocks. Let's say this is A plus 1, A plus 2, A plus 3. This is starting at B, B plus 1, B plus 2, B plus 3. This is C, C plus 1, C plus 2, C plus 3, dot, 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 right? So this way, if you're actually working on multiple arrays together, all of those arrays can be fed nicely into your cache, right? And actually, these contain data as well. So that now this is also a prefetch buffer, right? When a load misses in the cache, it checks the head of all the stream buffers. And if there's a hit, then it pops the entry from the buffer and updates the cache with the data and also uses that, right? If not, then it allocates a new stream buffer to the new miss address. Right? And these, let's say a load actually hits in the stream buffer, and the stream buffer, now you can actually bring in another cache block to the stream buffer, right? Let's say you have A plus, let's say this has 4 entries, A through A plus 3, and the load hits in A. Now you bring that block A into the data cache. Now you can bring in A plus 4 into the FIFO, right? So basically that's how you keep ahead of the processor access stream. It's a nice idea, and you can see how you can implement it. It's essentially a buffer, and you generate the next cache address, and when the core generates an address, you compare the head of the buffer to the address generated by the core. And this is from the paper, so it's the same thing. Does this make sense? Okay. So these are all regular access streams, if you will, and these, in various forms, these hardware prefetchers are implemented in the machines that you're using. In your laptop, for example, you have these hardware prefetchers that are prefetching for the, I don't know, maybe Facebook page you're surfing right now. Okay. Any questions? We will go into more sophisticated hardware prefetchers, but let's take a look at the performance. We've already covered this, kind of. Accuracy, coverage, and timeliness. These are 3 metrics that are important for prefetcher performance. And these are simple. I've already told you them, but you can look at their definitions also. Bandwidth consumption is another metric. Remember, the bandwidth off chip is a big limiter. So ideally, you would like to minimize the prefetcher's bandwidth consumption. This is essentially, if your prefetcher is inaccurate, or if it's too early, if you will, it can actually increase your bandwidth consumption, right? Because it generates wrong prefetches. One good news is you can actually use idle bus bandwidth to do prefetching. So if you have a prefetcher at the memory controller, the memory controller can see that, oh, this bank is not busy, and it can generate a prefetch for that bank. Assuming it's accurate, then this prefetch doesn't contend with other cache, other demand requests. And the other metric is cache pollution, if you will. These are the extra demand misses due to prefetch placement in the cache. And again, you would like to minimize this. Actually, you'd like to minimize the bandwidth consumption and cache pollution. And aggressiveness of the prefetcher that we've described here, how far ahead the prefetcher can stay in the demand stream, affects all of these metrics, right? If you increase aggressiveness, you can actually increase accuracy, potentially. You can increase, you can increase coverage, but you may actually reduce accuracy, right? You can increase timeliness, make it more timely, but you also increase bandwidth consumption, and you also increase cache pollution, right? Actually, there are two things in a prefetcher that make it more aggressive, right? For most hardware prefetchers, let's take a look at the stream or stride prefetcher. You have the distance, how far ahead can the prefetcher get from the demand stream. And if your stream buffer size is 4 cache blocks, the prefetcher can get 4 cache blocks ahead of the demand stream, right? And the prefetch degree. How many prefetches do you actually generate? Let's say the processor accesses A plus 15 and you know that the stride is 15. Do you generate 10 prefetches ahead? Or do you actually generate only 1? So if you look at this, let's look at this pictorial. You have the access stream. The processor accesses address X, cache block address X, and you have a distance. This is the predicted stream, if you will. And this is how far the prefetcher can get ahead. This is the maximum prefetch that it can generate. That's the distance. Now this distance could be very conservative. You can go ahead only a little bit. Now you can think about why this is bad for timeliness, right? It's not good for timeliness because the processor will access this soon, perhaps. But it's good for accuracy probably because maybe the processor will stop accessing the stream after this maximum address, right? You could be very middle of the road, if you will, make your distance a little bit larger, or you could be very aggressive, make your distance, I don't know, maybe 1,000 cache blocks ahead. Does that make sense? Okay. As you increase your distance, of course, your accuracy goes down. If you're 1,000 cache blocks ahead, maybe the processor will never get to it. Right? Degree is another thing, which is, let's say the processor is accessing address X. It accesses address X plus 1. How many prefetches do you generate? Do you generate 3? Or do you generate 1? Or do you generate 10? Right? That also affects the intensiveness of the prefetcher. Okay, so this is to summarize what we've talked about, basically. You can be very aggressive and well ahead of the load access stream, which hides memory latency better, but it's more speculative. Which means that it can have a higher coverage, because now you're prefetching more things, and better timeliness, because you're prefetching far ahead. The downside is likely has low accuracy, right? Because you're prefetching much more ahead and you're prefetching many more things. And higher bandwidth and pollution. If you're very conservative, then you're closer to the load access stream, which means that you may not hide the memory access latency. But now you're affecting demands less also. You're likely have a higher accuracy, lower bandwidth, you're less polluting with the prefetcher, but likely lower coverage and less timeliness as well. So these are fundamental trade-offs in prefetching. In fact, accuracy, coverage, and timeliness are all hard to get at the same time. If you want to improve coverage, you usually sacrifice accuracy. And you can actually try to design prefetchers. It's a very exciting research area too. How do you design a prefetcher that gets all of them? High coverage, high accuracy, high timeliness. It's the Oracle prefetcher. How do you design an Oracle for your program? Okay, so just to give you some data here, this is some data we had collected. This is accuracy of the prefetcher on the x-axis, and this is the percentage IPC change over no prefetching. IPC is instructions per cycle performance. So if you're not accurate, it's likely that you're going to reduce performance. So here, for this application, looks like the prefetcher accuracy is 5%. This is expressed as a fraction here. And the performance loss, IPC loss, is 50%. What does an IPC loss of 50% mean? Your performance degrades by 2x, right? Assuming your cycle time doesn't change. So accuracy is actually correlated with the performance you get. So we have a Not always though, because here you have a 100% accurate prefetcher, but performance improvement is not very high because the prefetcher may not be timely, right? So it could be polluting. So if you look at the effect of the prefetcher in terms of its aggressiveness and how much it improves performance, this is just one data point from the SPEC applications. SPEC is Standard Performance Evaluation Corporation, and they publish these applications where a lot of processors vendors benchmark their processors with. Maybe we can talk about benchmark in some other lecture. But if you look at the performance you get in terms of instructions per cycle on these applications, this is the geometric mean of IPC across all of these applications. Performance increases as you increase the aggressiveness of the prefetcher. So more aggressive, the better, on average. But the more aggressive you are, the worse you are on some benchmarks. These two benchmarks, for example, lose performance by about 50% if you're very aggressive compared to no prefetching. So you'd like to keep this under control. And one of the things that existing processors do is to throttle prefetches. What they do is, in some way, they monitor the prefetcher performance metrics, not necessarily exactly, but they try to get a hint of whether they're doing the prefetching the right things or the wrong things, or whether the prefetcher is consuming a lot of bandwidth when there are other things that need that bandwidth. And they throttle the prefetcher aggressiveness up or down based on past performance metrics. And that's the idea of prefetcher throttling. If the prefetcher has low accuracy, reduce its aggressiveness. If the prefetcher has high accuracy, increase its aggressiveness. Right. And you could actually consider other metrics here also. And I'll just give you an example decision process. This is just one example. For example, if the prefetcher has low accuracy, then and if it's polluting the cache, then you can decrease the aggressiveness. So if you have a prefetcher control mechanism like this, throttling mechanism like this, and I'm not going to go into this in detail, but the key idea is monitor how the prefetcher is doing based on its accuracy, timeliness, as well as coverage, potentially. In this case, we use accuracy and timeliness. And based on that, increase or decrease its aggressiveness. If you do this, then your prefetcher becomes even better in terms of performance. Remember these applications, they were losing performance because of aggressive prefetching. Now you can make them gain performance by appropriately adjusting how aggressive your prefetcher is. And overall, you can make prefetching even better by using this kind of technique. Okay, any questions before we part? We'll continue with prefetching and more memory next time.